This seems to be an area where people either really enjoy and understand or they struggle a bit. And it's about covalent bonding, which involves the sharing of electrons by two atoms. Now, most of us have learned already that covalent bonding occurs in non-metallic elements, and we can see it also occurring in the metalloids, or near the steps between metal and non-metal. So silicon and things like that are also part of this. Now, each of these things does it in its own way. The picture here shows graphite, which is an allotrope of carbon. An allotrope simply means just a different way of packing the atoms together, and it forms its own little pattern, as we can see, and it forms a sheet arrangement that is shown. When we looked at ions, we saw that the electron actually physically moves, or the electrons, if there's more than one of them, move from the valence shell of one atom to the valence shell of another. And this creates the ion, or the charged particle, and then we get electrostatic attraction between them. But what happens if we don't have enough energy present? Well, in this case, we actually have both atoms sharing the same electrons. And most of the time in here, we're going to be talking about the octet rule. In other words, trying to make sure that there are 8 electrons, a total of 8 in each of the shells. And this, of course, is not true for the first shell, where there are only 2. And we know that the bigger shells, like the third and fourth, have more than 8 electrons. But as you know, the highly stable elements of the noble gases have 8 electrons, and that's why we concentrate a little bit on the 8 or octet rule. And this works especially well for the first 20 elements. I suppose it's stating the obvious, but the non-metals combine, their electron shells or electron clouds overlap. And in the overlapping, the electrons can be used by both of the atoms simultaneously. And we say this is a covalent bond. Now, normally if we get a S subshell and another S subshell, 2 balls bumping into each other and overlapping occurring, we get a single covalent bond formed, because we've got 2 electrons being shared by the 2 atoms, which means 1 bond. So there must be, for a double bond to form, there must be 2 electrons shared in each bond, or a total of 4 electrons involved in the sharing process. So it's handy to remember that everything occurs in pairs. But we've also seen that not all elements are the same, and they all have a different pull on the electrons in the bond, if you like. Some of them have a much stronger pull than the others, and normally we use a thing called electronegativity, and this is an indicator of how strong a pull an atom has on it. And if we go right up into the top right hand corner of the periodic table to fluorine and chlorine, we find that the halogens have very, very high electronegativities, and this gives them their reactivity as well. So if we don't have even sharing of electrons, then we have a dipole formed. Now, a dipole means we have slight variation in charge between one end and the other end of the bond. Now, this allows other interactions to occur, particularly the intermolecular forces. So what we can do is we look at these things and try to work out what's going to happen, and then we can use it to try to explain the physical properties we see. Now, this works particularly well for things like water and other chemicals where we have this very, very strong polar nature. Depending on which textbook you read, the values shown here will vary. And they vary a little bit, but that's a good rule of thumb. This one I've given you is a rule of thumb that I've found. And it says if we look at the difference between the electronegativities of the 2 chemicals involved in a bond, we can see if it's going to be just a normal bond, which I've written down as covalent, if it's going to be a polar bond, or if it is going to involve electron transfer. So we're going to have an ionic structure forming. Now, the values above show the difference between the two. So if it's a difference of less than about 0.4, we just call it a covalent bond. There won't be any real charge on it. The forces that it's created, the attraction forces between neighbouring molecules, will be a little bit lower than this. So there's no real advantage for there's no real changes in the expected physical properties of it. However, if the difference between the electronegativities it increases and is above about 0.4 but less than about 2, then we find we get a polar nature. The closer it is to 2, then we're going to have almost one negative end and one positive end of the bond. And this produces a very strong dipole, and that will affect, as I say, the physical properties of the compound involved. Well, it can anyway. And we'll get more of that later when we look at electronegativities again and polarity a bit more detail. If the polarity is above 2, then we can class it as being ionic. Alright, how about we consider hydrogen chloride as our example? Now, I've got the two atoms here, and what I've done is I've looked at Table 8. I'll leave that there. Table 8 in our data booklet tells us that the electronegativity of hydrogen is 2.2 and the electronegativity of chlorine is 3.2, which gives us a difference of 1.0. Now, according to our scale, we just saw that would make it a polar bond. So let's put the bond in. So I put the bond in to start off with. So this means that if we took an electron picture, or were able to take a picture of electron distribution and density, we'd find a lot more electrons at the chlorine end of this. So there'd be a lot more electrons down this end of the bond and at this end of the bond. So with all the electrons down here, we actually give the bond a partial charge. Now we use the delta symbol, the slower delta symbol of this one, to show this is our negative end. And this actually means that the other end will be partially positive compared to it. So when we have this coming on, we now have a polar bond, and because there is only one bond in the molecule, we must have a polar molecule. We've actually set up a bit of a dipole going on here, and we can actually show it this way as well. We can actually draw a line in. Now, the positive end of our dipole, also a positive there, is the hydrogen, and the electrons are moving down this way. They're being pulled this end. And this is how we form a polar bond within a covalent molecule. So if you get a question like this in your test, especially paper 2, the most correct answer to the type of bonding in hydrogen chloride would be polar covalent. So if we use that, we should be fine. More about polarity and its effects in a later video.